4.2 integer representations. We certainly take our decimal number system for granted. A number written like this with digits 4, 3, 9, and 6. Well, we know what each of those digits represents. That's 6 ones, plus 9 tens, plus 3 hundreds, plus 4 thousands. So each digit is multiplied by a power of 10. And 1 counts as a power of 10. It's 10 to the power 0. So the digit on the right, that always represents ones. Then tens, 10 squared, 10 cubed. And these digits, so these are always between 0 and 9, so 1 less than the base. The base here is 10. And in this section we look at different ways to represent integers where we change the base. The base can be any integer, any positive integer, at least 2. Base 1 doesn't make sense. We're used to base 10, but in computer science, base 2 is very common, so binary expansions. Base 8 and base 16. Base 16, that's called hexadecimal, and base 2 is octal. Example 1. Convert the binary number 110101 to its usual decimal expansion. And this is the usual way to write. So if you look at different bases, then write the number like this and put the base here. So this is base 2. The digits, if you're in base 2, then the digits are just 0 and 1. Those are the only possibilities. So this one here, that represents 1, 1. Instead of tens, now we have 2s, so this is 0 2s. Instead of hundreds, it's 2 squareds, that's 4. No 8s, 116 and 132. Alright, so the base here is 2, so we're just using powers of 2. So again, the digit on the right represents ones. The digit just to the left of that represents the base itself, so your base 2. Then the base squared, base cubed. So add these up, you get 53. So this binary number represents 53. You could write 53 like this just to emphasize it's base 10, but we won't bother. These binary numbers, they're just bit strings that we've been working with, so strings of zeros and ones. So here's the general setup. So we write a base B number like this. So parentheses with a subscript B, and inside are the digits D0, D1, D2, up to DK. So this is a base B representation. These digits are between 0 and B minus 1. So as we saw for base 2, it's 0 or 1. Base 10, it's 0 through 9. For bases bigger than 10, you're going to need some extra symbols. And this number represents, well, this is the representation for this number. So D0, that number of ones, plus this digit times the base, plus the next digit times the base squared. Example 2, find the decimal representation of this number, 2470, and this is a base 8 representation, so an octal number. Well, yeah, we can just write it like this. And so 0 ones, 7 eights, so 7 times 8. 4 times 8 squared, that's 4 times 64. 2 times 8 cubed. And then add those together to get the number in the usual representation. So 1,336. Okay, so it's pretty easy. So if you're given a number in another base, then yeah, you're just using this formula. Multiply the digits by powers of the base to get the number in the usual format, base 10. But how do you go in the other direction? So how would we have converted 1336 to base 8? Well, instead of multiplying, now you're dividing by the base. So here's how it works. Yeah, so we're just using the division algorithm, looking for quotients and remainders. So take the number we want to convert and divide it by the base, divide by 8. Okay, so just doing it by hand here. So here's the quotient, 167. Here's the remainder. Now take the quotient and divide that by 8. So we get a new quotient and a new remainder. And then, yeah, so just keep dividing these quotients by the base. So new remainder 2, new quotient 2, remainder 4. Keep doing that until you get a quotient of 0, and then you can stop. Well, you could keep going, but you just get a bunch of zeros. And it's these remainders that give the digits. So yeah, you can see them here. So this is the number we're expecting, 2470 base 8, and here's the 2470. Okay, so they come out in reverse order. So so this is the number of ones, 8s, 8 squareds, 8 cubes. All right, so yeah, another application of the division algorithm, quotients and remainders. And we can see why that makes sense. Yeah, just in this example, so for the original number, yeah, dividing by 8, we get this quotient, and the remainder was 0. Then we take the quotient and divide it by 8. We get quotient 20 and remainder 7, so we can, so the division algorithm lets us write 167 like this. Then the 20 is 8 times the new quotient 2 plus 4. And then if we expand this out, so keep all these 8s. Yeah, so it's 8 times 8 times 8 times 2. This 4 is just getting multiplied by these two 8s. The 7 is just getting multiplied by 1 8. Alright, so that's our base 8 representation. Yes, so we need 2470. But but it's easy to remember the algorithm, so just keep dividing these quotients by the base, and the remainders give the digits. Just make sure you write them in the correct order. So another example, yeah, let's use base 7, convert 988 into base 7. So divide by 7, we get quotient 141, remainder 1. Then divide that quotient by 7. We get a new quotient 20, remainder 1. Divide that quotient again. New quotient 2, and then divide that 2 by 7, the quotient 0, so then we stop. And these were the remainders. So we're getting 2611 for our base 7 representation. Yeah, notice I'm not reading this 2611 because it's not 2000 or 600. It's, instead of thousands, it's 7 cubes. Instead of 600s, this is really 649s. So and also, yes, something we've noticed before, if you divide by 7, then the possible remainders have to be strictly less than 7. So 0 through 6. Okay, so these remainders, yeah, you're never going to see 7s or 8s or anything higher. So these digits are always between 0 and the base minus 1. Yeah, I should say that these representations are unique, so yeah, as long as you have this restriction on the digits, then there's only one way to write each number. Just like, there's only one way to write numbers in the usual base 10. Let's look at that bigger base. So for base 16, we need more symbols. So we can use the usual symbols, 0 through 9, for those numbers, but for 10 through 15, we need new symbols, and it's standard to use just capital A, B, C, D, E, and F. So here A means 10, B is 11, C, D, E, F is 15. So if you write a hexadecimal number, it can use the digits 0 through 9, but also it could have these letters showing up. Example 4, convert A8FC in base 16 to binary, base 2. Well, one way to do that is to convert this number to base 10 first. So we have C1s, that's 12 ones. We have F16s, that's 15 16s. We have 8 16 squareds, and A 16 cubes, where A again means 10. So if I did this right, that's so this hexadecimal, its base 10 representation is 43,260. Alright, so that's a fairly big number. So converting that to base 2 is a bit of work. Alright, so we just keep dividing this by 2's, getting quotients and remainders, and then divide the new quotients by 2. Alright, so we get this, keep going until the quotient is equal to 0, then you can stop. And reverse the digits, so this is the leftmost binary digit, the leftmost bit. Okay, so we get this answer. So this is the binary version of this base 10 version and this base 16 version. Okay, yeah, so certainly this is good for a computer to do. But there was a better way to do this by hand. It's easy to convert hexadecimal directly to binary. So take the hexadecimal digits A, 8, F, and C, and just convert each of those to their binary representations. So A is 10, and 10 in binary is 1010. So no 1s, 1, 2, and 1, 8. 8 is 1000 in binary. 15 is all 1s, and 12 is 1, 8, and 1, 4. And then each of those, so each hexadecimal digit is really a 4-digit binary number itself. So use these pieces to get the binary representation. Okay, so you can see it's the same number we got doing it the long way. Yeah, so since hexadecimal, it's 16, it's 2 to the power of 4. It's directly connected like this to binary. And you can use this shortcut whenever you have one base a power of another. So we can also use it if we're converting between octal base 8 and binary. So an octal digit represents 3 binary digits. So in this example, convert 1011101 base 2 to octal base 8. Okay, so we're just going to group. So starting on the right, group these bits in groups of 3. So this this part is going to give us our first octal digit. So what is this binary number? So it's 1 1 and 1 4, so that's 5. The second piece is 1 1 and 1 2, that's 3. And this is just 1 1, that's 1. So the octal version of this binary number is 135 in base 8. Yeah, we're in base 8. We just need the digits 0 through 7, so we don't need any A's or B's. Alright, so we can look at some more examples in the book, but that's all we're looking at in this section. Alright, so here's the expansion in base B. To convert this binary number into its decimal expansion, just multiply the digits by powers of 2. For this octal number, multiply by powers of 8. And for hexadecimal, it's powers of 16. And just remembering again, so maybe starting on the right, so this B, so remember, A is 10, B is 11, so this is B1, so 11 ones. This 0 means 0 16s. E is 14, so that's 14 times 16 squared. A is 10, 10 16 cubes, and one more digit, 2 16 to the 4th powers. So multiply and add those together, that's 17 or 175,627. Okay, and in the other direction, you're using the division algorithm, so keep dividing by the base, getting quotients and remainders. So 1, 2, 3, 4, 5, 12,345, converting that to base 8. So divide by 8 and get a quotient and remainder. Then divide the quotient by 8, new remainder. Keep going until the quotient is 0. And then these remainders give the digits, the base 8 digits. Yeah, the last remainder you get, that goes on the left. The first remainder goes on the right. Here's one converting into hexadecimal. So you're dividing by 16s. And yeah, when you divide by 16, the remainders go from 0 to up to 15 is possible. And then just remember, these numbers that are 10 or higher get a letter. So 11 is B, 14 is E, 10 is A. So we get this hexadecimal number. Here's a binary one. Alright, so yeah, I did want to mention bytes. So bit strings of length 8 are called bytes. So this is an example of a byte here, and they have a nice representation as just a 2-digit hexadecimal number. So this is convenient. So yeah, so it's kind of awkward dealing with binary numbers. It's much more convenient to use hexadecimal. Certainly more compact. Okay, so that's a quick look at changing bases.